We are now on section 7.2, covalent bonding. Here we're going to describe the formation of covalent bonds and define electronegativity and assess the polarity of covalent bonds. So covalent bonds are formed from the mutual attraction of atoms for a shared pair of electrons, not a shared par. So what ends up happening is you have nonmetals with some similar ionization energies and electron affinities that become attracted to each other. And they end up sharing electrons to form these covalent bonds and covalent compounds. These compounds have very different properties than ionic compounds. They tend to have lower melting and boiling points, and this is to the point that some of them are liquids, solids, or even gases at room temperature. Their solids tend to be softer than ionic solids. They're very poor conductors in any state of matter, and a lot of them are not soluble in water. So most ionic compounds are soluble. Of course, we have our solubility rules, but covalent compounds, a lot of them are not soluble in water. Let's talk a bit about how these bonds are formed. And we're going to do that by looking at the formation of the H2 hydrogen molecule. We start off with two separate hydrogen atoms that have some somewhat high potential energy, and they begin to approach each other. So as they get closer and closer, their valence orbitals, those 1s shells, start to overlap with each other. And then that forces the electrons to start interacting with the other nuclei. These electrons now get attracted to the other nuclei, and it starts to stabilize the system, decreasing the potential energy as that distance between the nuclei, as our bond distance, is decreasing. Eventually, they get to a certain distance where if the nuclei try to get closer to each other, that potential energy goes back up due to the positive nuclei repelling each other. So the distance at which you have the lowest potential energy is used to determine the actual bond length between two atoms. And just a reminder, energy needs to be added to break a chemical bond. For example, if you want to try to break a molecule of hydrogen into two individual hydrogen atoms, you have to put in 436 kilojoules of energy. Whereas energy is released when a bond is able to form. So when two hydrogen atoms come together to form a hydrogen molecule, it releases 436,000 kilojoules of energy. So this is a nice picture to show you what's going on with the energy as this hydrogen molecule forms. We're starting on the right and moving to the left as far as time is concerned. So when our atoms are separate, okay, they have some energy. We're calling it kind of the 0 point of energy. This is kind of an arbitrary point. But as they get closer together, you see this energy starts to go down. Eventually, it reaches a point where it rapidly goes down. And then it hits this minima as the two atoms reach this ideal bond length. But if they try to get closer together, then that energy starts to go up very quickly due to those positive nuclei repelling from each other. So let's talk about the types of covalent bonds. A pure covalent bond, this is also called a nonpolar covalent bond. This forms when electrons that are being shared have equal probability of being near each nucleus. For example, the chlorine molecule, you have two chlorides bonded to each other. They're the same, so it's a pure covalent bond. The electrons, there's neither of them that it's going to favor because they're the exact same. So the electron has the same chance at being around either atom. Each chlorine has 6 non-bonding electrons, called lone pairs, and 2 shared electrons, or bonding electrons, give each a total of 8 electrons, matching the valence of argon. Don't worry about what non-bonding versus shared electrons means at the moment. We will talk about those a little later. So the nonpolar, nonpolar, poles meaning opposite. Nonpolar means that they're the same, right? So they're not opposite. Whereas if you have two atoms in a covalent bond where the electrons are not shared equally, you have a polar covalent bond. So one atom attracts the electron more than the other, making the electron density shift towards it. So the chlorine molecule, you have your two chlorine atoms. The electron density would be kind of in the white there. The electron has the same chance of being in around either one. Kind of looks like a face. I'll give it a smile. In a polar covalent bond, something like hydrogen chloride, you have your hydrogen atom and your chlorine, but the chlorine attracts those electrons more. So if we were to draw a probability of the electrons, it's going to look more like this, where that white space is the electron density or the probability of where you're going to find the electron if you were to take a snapshot of this molecule. So this guy here, a little confused, right? Those electrons are more attracted to the chlorine. So what ends up happening because of this, and because the chlorine in this bond has more of the electron density around it, it ends up having a partial negative charge. It's not enough where we could say it's a full negative charge. This is not an ionic compound. So it's not like it's a -1 or -2. It's some fraction of that. It's a partial charge. So we denote that by using the Greek letter delta and then a minus sign to say this is delta negative. It's the partial negative. And because remember, our molecules, unless there's an overall charge to it, they have to be neutral. So that means we must have some delta positive. And that's going to be on, in this case, the hydrogen end, the side with the least electron density. The other thing that is often used is an arrow with a cross on the end, and this denotes the movement of the electron. So for hydrogen chloride, the arrow with the arrowhead would be pointing at the chlorine to say this is the more electronegative, the side that has the more electron density, with the partial negative, and the partial positive sign has this little cross through the end, so it kind of looks like an elongated plus sign. So that tells you where the partial positive and the partial negative are. Now, this will probably come more into play next week, but this arrow, for those that are curious, is called a dipole arrow. So this is a much better drawing than what I can do, showing you the electron density around hydrogen and chlorine and their partial positive and partial negative charges, as well as the dipole arrow. So to figure out the actual polarity of a bond depends on the electronegativity of the bonding atoms. And this is a measure of the tendency of an atom to attract electrons or electron density towards itself. The stronger it's able to attract atoms, the higher it's able to attract electrons, the higher its electronegativity. So if you have a stronger electronegative atom, it's going to have the partial negative charge in a polar covalent bond. The greater the difference in electronegativity, the more polarized your molecule is, which means the greater you have these greater partial charges. It is not to be confused with electron affinity that we talked about in chapter 6, I believe it was. Electron affinity is something we can measure, and you look at it in terms of kilojoules per mole. However, electronegativity is dimensionless and it's an arbitrary scale. It's calculated, it's not measured, and it ranges from 0 to 4. So your book gives you a really nice table with electronegativities on it. Notice there's no noble gases, and that's because in general, noble gases don't form compounds. Yes, there are exceptions. Yes, we will look at some of them when it comes to structures. But overall, we don't worry about their electronegativity. But you can see something like fluorine is the most electronegative atom. It really likes those electrons. And overall, the nonmetals have fairly high electronegativities. Compare that to the metals, or non-metals have this high electronegativity. Our metals have a low electronegativity because they don't want electrons. They want to get rid of them. So cesium and francium here have our lowest electronegativity. They really don't want those electrons. Non-metals want them, metals don't. Linus Pauling, he's just a big contributor in chemistry. He actually has received 2 individual Nobel Prizes. He literally didn't share them with anyone. He's won one in chemistry for his work on the nature of chemical bonds, and the other one, he actually won the Nobel Peace Prize for his opposition to weapons of mass destruction. So, pretty cool dude. So let's talk about electronegativity and bond type. When you take the difference of your electronegativities, you can then predict the type of bond it is based off of the value you get. Okay, so your book calls this delta En. You just take the absolute value of the difference. If you have a very small difference up to like 0.4, this is considered a pure or a non-polar covalent compound. Okay, non-polar meaning there's really not much, there's no difference between the electronegativity. If it's between 0.5 and 1.8, it's usually a polar covalent compound, and greater than 1.8 tend to be ionic compounds. And these are very rough numbers. They're not perfect. There are some compounds, some covalent compounds that have a very, very high electronegativity difference, but they're still covalent because it's still a non-metal bonded to a non-metal. One example is hydrogen fluoride has an electronegativity difference of 1.9, but it's still a polar covalent compound. It's not an ionic compound. Overall, your best guide to determine if a compound is covalent or ionic is to look at what's bonded. An ionic compound is a metal and nonmetal, or cation and anion. A covalent compound is a nonmetal and nonmetal. We can have compounds, of course, with both covalent and ionic bonds. This is where polyatomic ions come into play. So the polyatomic ions are held together by covalent bonds. For instance, OH minus, NH4 plus. Now, these are just some examples. NO3 minus. These are each held together by covalent bonds, generally polar covalent bonds. And then they have that overall charge for it to then bond with a cation, or in ammonium's case, an anion. So this is just a little table kind of going over the electronegativity differences and the different bond types. Here's an example. Bond polarities play a very important role in determining the structure of proteins, and we are going to look at some bonds and order them in order of increasing polarity and figure out which ones are the partial negative and partial positive. So we have CH, CN, CO, NH, OH, and SH. What we need to do is we look at the electronegativity table to do this, and we see that carbon's electronegativity value is 2.5. Hydrogen's is 2.1. Nitrogen is 3.0. Fluorine is 4.0. And sulfur is 2.5. So the carbon-hydrogen bond, that change in electronegativity, is equal to 2.5 minus 2.1, so that's 0.4. Carbon-nitrogen is going to be equal to absolute value of 2.5 minus 3.0, that's 0.5. Carbon oxygen equal to 2.5. Oops, I forgot to put oxygen on here. Oxygen is 3.5. Carbon oxygen, then 2.5 minus 3.5, 1.0. Nitrogen hydrogen is equal to 3.0 minus 2.1, 0.9. Oxygen hydrogen, 3.5 minus 2.1, that's 1.4. And sulfur hydrogen, 2.5 minus 2.1, 0.4. So we see that carbon hydrogen and sulfur hydrogen have the lowest electronegativity differences. And for the carbon hydrogen bond, carbon is more electronegative, which means it has the delta negative, hydrogen has the delta positive. For sulfur hydrogen, sulfur again has the higher electronegativity, so it's the delta negative. Carbon nitrogen is the next lowest or highest. Carbon has the lower electronegativity here, so it has the partial positive. Nitrogen with the larger electronegativity has the partial negative. And then you can see the trend as we go down.